Hello everyone and welcome to Reinforcement Learning Tutorials. In this tutorial, I will explain you an iterative policy evaluation algorithm. I will explain you how to implement this algorithm in Python, and at the end of this video, we will test the performance of the iterative policy evaluation algorithm in the Frozen Lake environment from the OpenAI Gym. As always, I created a post that nicely summarizes everything that I will explain in this video. This post contains all the explanations, graphs, and it even contains Python codes that you can see over here. A link to this post is given in the description below. And before I start, I would like to mention the following. It took me a significant amount of time, energy, and planning to create this video and this post. Consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. Okay, so let's start with the required previous knowledge. Before watching this video tutorial, it's a good idea and I strongly suggest you to go over the following topics. First of all, you need to become familiar with the value function and its Bellman equation. Luckily, I created a post and even a YouTube tutorial that summarizes these important topics. So you can click over here, you can follow the link, and you can read this post that summarizes the value function and that explains the Bellman equation. Then, you need to become familiar with state transition probabilities, actions, episodes, rewards, and you need to become familiar with the OpenAI Gym library. You can learn these topics by following the second link. And here's the post. And here are two YouTube video tutorials. Then, you need to become familiar and to gain experience in using the OpenAI Gym library. And again, you can click on this link and read the post that will teach you how to use the OpenAI Gym library. Okay, under the assumption that you obtained enough background information and background knowledge, we can continue with this YouTube tutorial. So let's start with the motivation. The iterative policy evaluation algorithm is used in reinforcement learning algorithms to iteratively calculate the value function at certain states. Let us repeat this motivation once more, since it's very important from the beginning of this video that you get the main points. For a given policy, or better to say, for a given control policy, the iterative policy evaluation algorithm is used to iteratively calculate the value function at certain states. And this algorithm is a building block of more complex reinforcement learning algorithms. That's why it's very important to completely understand all the ingredients of this algorithm. So let us immediately jump on a test example in order to make this video more interesting. To test the performance of the iterative policy evaluation algorithm, we consider the Frozen Lake environment in OpenAI Gym. A detailed tutorial dedicated to the OpenAI Gym and Frozen Lake environment is given over here. You can follow this link to learn more about the OpenAI Gym and the Frozen Lake environment. This environment is illustrated in this figure. The Frozen Lake environment consists of 16 fields. That is, we have a grid of 4 by 4. To every field, we associate a number. Here's the number 0. This is the field 0. Here's the field number 1. Here's the field number 2. And the final field is the field 15. That is the field given over here. Then There are four types of fields. The first type is the start field, here or over here. Then we have frozen fields, F, here are the frozen fields. Then we have holes, here are the holes. And finally, we have the goal field over here or sketched over here. The goal of the game is to reach the goal field G starting from the start field S and by avoiding the hole fields. For example, a successful game can look like this. We start from here, we go down, then we turn right, then again we go down, and we reach our destination or our goal field. Here, it should be kept in mind that if you're at the frozen field, for example over here, we can only move left, right, up, or down. We cannot move diagonally. So this movement is not allowed, or this movement is not allowed. The game ends unsuccessfully if we step on the whole field. For example, if we start our game from here, we go right and then we go down and we step on the whole field, we end our game unsuccessfully. And finally, let's talk about rewards, since reinforcement learning is all about rewards. If we step on the frozen field, that is, if we step over here, we get a reward of 0. Similarly, if we step on the whole field, we also get a reward of 0. And if we step on the goal field, that is, if we end our game successfully, we get a reward of 1. With every field, we can associate a state. For example, with this field, we can associate state S1. With this field, we can associate the state S2. With this field, S3. With this field, S4. And finally, with this field, S16. After introducing the Frozen Lake example, we are ready to briefly summarize the value function and to relate the value function with the Frozen Lake example. So, what is a value function? The value function of a particular state S under the policy pi, denoted by v in the index pi of S, is the expectation of the return gt obtained by following the policy pi and starting from the state S. Here is the equation that defines the value function. gt is the return. You can think of the return as the sum of the rewards starting from rt plus 1 plus rt plus 2 and until the end of the episode or until the end of the game, where rt plus 1 is the reward obtained at the state st plus 1, rt plus 2 is the reward obtained at the state st plus 2, etc. Here, it should be kept in mind that the value function of the terminal state is defined to be 0. So what are the terminal states? Going back to our example, that is to our frozen lake, the terminal states are the states that terminate the game, and these states are obviously the whole states and the final or the goal state. Let us go back to the Frozen Lake example. To every field, that is to every state, S1, S2 until S16, we can associate the corresponding value function. Here is the value function of the state S1. Here is the value function of the state S2. Here is the value function of the state S3. Similarly, here is the value function of the state S16, and the state S16 is the goal state. A very important equation that enables us to iteratively compute the value function is the Bellman equation. The Bellman equation is given by the equation number 2. Let us briefly explain the true meaning of the Bellman equation. And let us consider our Frozen Lake example. Let us assume that we are in the central field. That is, that we are in this field. And let this field, or better to say, its state, be denoted by S. Then, let us assume that we are following the policy pi selecting A, given that we are in the state S. So this is actually a probability of choosing a particular action A, given that we are in the state S. We have 4 possible actions. We have action A1 going up, action A2 going down, action A3 going left, and the action A4 going right. This graph corresponds to the sum over here. So the summation is performed over A1, A2, A3, and A4. Next, let us assume that we are in the state S and that we selected the action A2, that is, go down. And let's see what are the possibilities. Since the system is completely probabilistic, or better to say stochastic, even if we are in the state S and we selected the action A2, that doesn't mean that we will necessarily go to this state, that is, to the below state. Since this is a frozen lake, the floor is very slippery. If we want to go down, it might happen that we in reality can go left or right. That is, there is a certain probability of going to this field or to this field if we selected the action go down. Of course, there is a certain probability of going to our intended destination, or there is a certain probability of even going upwards. These probabilities are encapsulated or governed by this probability that's called the dynamics of the Markov decision process. Again, probability pi, given that we are in the state S and that we selected the action A, is the probability of reaching the state S prime and obtaining the reward R in that state, given that we are in the state S and given that we have selected the action A. S prime is our final destination state. So this can be S prime, or this can be S prime, this can be S prime, and this can be S prime. For example, to this particular case, we can assign this probability to be equal for all of these S prime. Let's call this S prime 1, let's call this S prime 2, S prime 3, and S prime 4. So the probability of reaching of any of these states, S1 prime, S2 prime, S3 prime, and S4 prime, given that we are in the state S and that we have selected a particular action, let's say the action A2, can be, for example, 0.25 or 1 over 4. So there might be an equal chance of going to any of these fields if we were in this field and if we selected the action go down. Then, by reaching the particular state S prime, we obtain a certain reward denoted by R, and we have a certain value function at that destination state. And this value function is denoted by V pi of S prime. And finally, we are ready to give a summary of the Bellman equation. For that purpose, let us consider the Frozen Lake environment. This is our central field, and let us consider the 4 neighboring fields. The current state is this state S, and we have 4 possible next states. These states are S1 prime, S2 prime, S3 prime, and S4 prime. To every next state, we can associate a value function. So this is value function at S4 prime. This is the value function at S1 prime. This is the value function at S2 prime, and this is the value function at S3 prime. The Bellman equation enables us to compute the value function for this central field or for the current state on the basis of the value functions defined for all possible future states, and on the basis of the reward obtained by going to the future state, and on the basis of the transition probability, or on the basis of dynamics, and on the basis of the policy. Now we are ready to explain the iterative policy evaluation algorithm. The goal of this algorithm is to compute the value function for every state, and this value function is expressed by using the Bellman equation. Or better to say, we use the Bellman equation to compute the value function. Let us assume that we have n states, S1, S2, S3, until Sn. For every state, we can write the corresponding Bellman equation. For example, for the state S1, we can write value function pi at the state S1 is equal to the right-hand side. And for simplicity, I'm not going to write the right-hand side. It's important to note that the right-hand side will be again a function of the value function. Then we can write the value function for the state S2. And we can use the Bellman equation to express the right-hand side. Again, here I will write 3 dots. By repeating this process, we will end at the value function at the state Sn. And again, we can use the Bellman equation to express the right-hand side. Let us analyze these equations. We have a system of n equations. So what are the unknowns in these equations? Well, the unknowns are the value functions defined at particular states. That is, the unknowns are V pi of S1, then V pi of S2, 3 dots, until V pi of Sn. Under the assumption that the transition probabilities or that the dynamics of the system is known, and under the assumption that the reward values are known, and under the assumption that this coefficient is known, and under the assumption that the policy is known, we obtain a system of n equations with n unknowns. And since this is a linear system, under mild assumptions, we can solve this system and we can compute the value functions at the states S1, S2 until Sn. This was one approach for solving this system. However, there is another approach that, in my opinion, is more elegant. And this approach relies upon an iterative solution. So what is the idea? In order to explain the main idea, let us consider a fixed point iteration. Let us assume that we want to solve the following nonlinear equation. X is equal to f of x, where f is a nonlinear function. How to solve this equation? Of course, we can, for example, use Newton's method. However, is there a more elegant and more numerically tractable way for solving this equation? Of course, there is such an approach. Under some mild assumption, we can define the following iteration. Xk plus 1 is equal to f of xk. By initializing this iteration with some x0 and by propagating this iteration, the value of xk, when k goes to infinity, will approach to a true solution. That's denoted by x star. Again, here is the idea. We start the iteration with x0 and we compute x1 simply as f of x0. Then in the next step, k is equal to 1, we have the following. We compute x2 as f of x1, where this x1 is the x1 computed from the previous iteration. And we continue this process, and for sufficiently large k, our xk will converge to the true solution. Again, the convergence is not always guaranteed. It depends on the properties of this function f. However, in the case of the Bellman equation, we can use this iteration, that is, we can use the fixed point iteration to iteratively solve the Bellman equation, that is, to compute the value function. Okay, so let's use this trick to solve our Bellman equation. What is the main idea? The main idea is to transform the Bellman equation into an equation that's iterative. And here's the result. So what did we do over here? We simply included an index k over here and an index k plus 1 over here. And here is the iteration. And this equation is in the core of the iterative policy evaluation algorithm. At the iteration k is equal to 0, we simply initialize the iteration with a guess of the value functions. And we guess the value function of every state. And then we simply propagate this iteration until convergence. Here, it should be kept in mind that the value functions of the terminal states should be initialized as zeros. So keep in mind this fact. In order to implement this algorithm in Python, we group all the value functions, that is, the value functions of all the states in the vector vk. Okay, so what is the idea for implementing this algorithm in Python? Well, we can split our iteration into two sums. Be careful here. I said two sums. However, going back to the original form of our iteration, that is, by analyzing this equation over here, we can observe that we actually have three sums. We have the sum over A, the sum over S prime, and the sum over R. However, in the particular example that we are considering, that is in the case of the Frozen Lake example, the sum over R does not exist, since the dynamics, that is, this probability over here, does not include R, since we assume that the rewards are deterministic. So P S prime, comma R given S and A is equal to probability of S prime given S and A. Consequently, we don't need to sum over R. And this fact significantly simplifies the implementation. Consequently, over here we will have the outer sum, and this sum will be performed over the actions, and then we have the inner sum that will be performed over the next states. Here's the Python implementation of the iterative policy evaluation algorithm. As you can see, I'm using the spider environment in Anaconda. I like spider very much since it reminds me of MATLAB. I can simply select certain code lines, I do the right click, and I can execute these code lines. As always, the first step is to import the necessary libraries. We import the gym library, we import the plotting tools, then we import this nice library for plotting, Seaborn, and finally we import the NumPy. So let us import the libraries. Next, let us create our environment. We call the function gym_make, we specify the name of the environment, and we specify the render mode. Let's do that. Nothing happens. Of course, nothing happens because we have to reset the environment. Then we need to render the environment in order to visualize our problem, and let us find the rendered environment. Here is the rendered environment. It hides from us. However, we will not need actually the graphical user interpretation of our environment. Consequently, we can simply close the GUI. That is, we can close the graphical representation of our environment. Okay, let us look into the observation space. That is, let us check the number of states. Good, we have 16 states. That's what we expected. Then, let us check the action space. We have 4 actions. These actions are up, down, left, and right. Good. Everything is as we expected. The next step is to inspect the transition probabilities. So let's go back to our post and let us investigate this probability over here. Let us analyze this probability. We can access this probability by simply typing environment. The first argument over here is the state argument, and the second argument is the action argument. When I write P01, I'm asking OpenAI Gym to provide me the dynamics, or better to say, the transition probabilities of being in state 0 and selecting the action 1. By typing this code line, we asked the OpenAI Gym what is the transition probability of being in this state, and by applying the action down. Let us analyze the result. Here is the result. We obtain a list with 3 elements. The entries in every element should be interpreted as follows. This part over here is our transition probability. This part over here is the next state. This part over here is the reward, and this false over here is actually a Boolean variable that provides us an answer to the question, is the next state terminal state? In this case, the next state is 0, and this is obviously not a terminal state. So the interpretation is the following one. We are currently in the state 0. So we type P and we have 0 over here. This number over here, 1, is the applied action. The applied action is going down. The next state is given over here, is 0. And this number over here is the transition probability. So this probability is equal to 0.33, and 33 repeats itself. So there is a chance of 1 over 3 of staying in the state 0 if we were in the state 0 and if we apply the action down. Again, there is a probability of 1 over 3 of staying in state S0 if we were in the state S0 and if we applied the action down. Let us analyze this transition probability. So what's happening over here? Again, we have probability. The current state is 0, the action is 1, which means down. And the next state is the state 4, as we can see over here, and the transition probability again is 1 over 3. Okay, so let us go back to our graphical representation and let us represent this graphically. So there is a probability of 1 over 3 of going to this state is the state 4, if we were in the state 0 and if we applied the action go down. Now that we verified the transition probabilities, we can proceed with the implementation of our algorithm. The first step is to select the discount factor, and the discount factor is this number over here. It's the number gamma. Usually we select this number in the interval from 0 to 1. In my case, I selected gamma to be 0.9. Then we initialize the vector storing value functions for every state. That is, we initialize this vector over here. We select every entry of this vector as 0. So every entry is equal to 0. Then we select the maximum number of iterations k. In my case, it's 1000. Then we select the convergence tolerance delta. The convergence tolerance delta is 10 to the minus 6. As you will see later on, the algorithm converges quite quickly. Next, we initialize a list that will track the convergence of the algorithm. This list will be used for visualization purposes, as you will see later on. This part over here implements our iteration. Let's go back to our iteration once more. What do we have over here? Obviously, we need to iterate over k. Then, for every fixed k, we need to compute the outer sum, and to compute the outer sum, we need to have a for loop that will go over the actions a. Then, for fixed a, we need to have another for loop that will evaluate the inner sum, and this for loop will iterate over s prime. That is, it will iterate over the next states. Okay, so here is again our code. This for loop over here iterates over k, that is, it will compute vk plus 1, the vector containing value functions for the next iteration. This for loop iterates over the states in our environment. In our case, this state variable goes from 0 and it ends at 15. Then we need to compute the outer sum. To compute the outer sum, we need to iterate over the actions. So this for loop iterates over the actions. And finally, we need to compute an inner sum. That is, we need to iterate over the next states. And this for loop iterates over the next states, s prime, and it computes the inner sum. Finally, over here, we test the convergence. If the difference between basically vk plus 1 minus vk is small enough, we stop the convergence. That is, if this difference is below the convergence tolerance, we stop the algorithm. Here are a few important comments related to this algorithm. Let us first focus on this part over here. This part is my probability of selecting a certain action. In my case, I'm assuming that all 4 actions are equally possible. That's why you have here 0.25. This part over here computes the inner sum. And again, the inner sum is defined over here. Now we are ready to run the algorithm. I will simply select this part, do the right click, and converged. I obtained the message that my algorithm converged. So let us visualize the results. I defined this function over here to visualize the results. Basically, this function will take my vector vk and it will transform this vector into 4x4 grid and do a plot, or do better to say a heat map that will visualize the values of the value functions. So let us see the result. Here it is. Here are my value functions. This is the value function for the state S1. This is the value function for the state 1, 2, 3, 4, 5, 6, 7. So this is V pi S7. And here you can observe that the value functions for the terminal states are zeros. that's a good check that can verify the accuracy of your implementation. Consequently, we have accurately implemented the algorithm, since we can see over here that the value functions in terminal states are 0. And you can simply verify that these states are actually terminal states by going back to our graphical representation and by looking at the structure of the frozen fields and the whole fields. Obviously, here we have a terminal state, here we have a terminal state, and these three states are the terminal states, and this corresponds to our results. And finally, let us plot the convergence. Basically, this graph plots the 2 norm of the vector vk, that is, we plot the Euclidean 2 norm of vk, that's represented like this, and we can see that after 6 or 7 iterations, our algorithm converges. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.